In this problem, they give us a value of K and a balanced chemical equation along with some information about the initial numbers of moles in a reaction vessel. And from that, we're asked to calculate the concentrations of all species once equilibrium has been reached. Let's start with a good expression for K, and we'll also consider Q in this case because they give us a concentration for each of three substances in the equation, and nothing has an initial concentration of 0, so we actually have to work out K. So let's start with the expression for Q. It's always going to be calculated the same way as you would for K, except we're dealing with initial concentrations rather than final concentrations. Note that there's a coefficient 2 in front of HI, hydroiodic acid, and because of that coefficient, we include an exponent 2 when calculating. The subscripts of 0 in the expression for Q simply indicate initial concentrations. It has nothing whatsoever to do with the mathematical application of that expression. Okay, next let's write an expression for K. This time I will not put a subscript 0 because it's implied if you write just brackets around a chemical substance that you're dealing with equilibrium concentrations. Of course, that's not always the case, but if you don't otherwise specify, then the assumption is that we're dealing with equilibrium. Okay, now let's give a good ice table. Notice in the problem, they tell us that we have 1.0 moles of each of three substances, and conveniently, the volume is 1 liter. So if you just take the number of moles and divide by 1, you'd have the molarity. And since that doesn't change the number, it's going to work out to be 1.07 for each of these. Now here's where it gets interesting. Whereas in most equilibrium problems, one of the initial concentrations is 0. And that tells you that you would shift to the side with the 0. But in this problem, we have actual numerical values that are not 0 for each of the three substances. So we've got to calculate Q. That's okay. It's not the end of the world to calculate Q. We're just going to plug in the 1.07 molar for hydroiodic acid over 1.07 for hydrogen and 1.07 for iodine. And you know what? Everything's going to cancel out and Q works out to be 1. Now, if Q is 1 and they tell us up above that K is 100, what do we know about the comparison of Q to K? Well, 1 is less than 100, so Q is less than K, and that means we shift right. For us in the ice table, all that means is put your pluses on the right side of the equation and put your minuses on the left side, at least in the change line of the ice table. We'll define that change in terms of x, and if there's a coefficient, like we see with hydroiodic acid, that carries down. Important not to forget that. It's plus 2x for HI. And then at the equilibrium line of the ice table, we're just adding together the initial and the change to give us an expression for the equilibrium concentration in terms of x. Now, we have a value for K and we have expressions for the equilibrium concentrations in terms of X. Why don't we plug in? So up above we had worked out a nice equilibrium expression. Don't forget the exponent too. And I think you'll see that once we plug in these expressions for X, that we have a perfect square. So in the numerator we have something that's squared, and if you multiply the two items in the denominator you'll get 1.07 minus x squared. All of that is equal to the value of k that they had given us at the beginning of the problem, which is that k equals 100. So now we've got a nice expression which we can take the square root of. If we take the square root of both sides, we'll get a, let's see, on the top, 1.07 plus 2x, because you get rid of the square. And on the bottom, 1.07 minus x. The square root of 100 is 10. And it's algebra from here on out. You just need to find the value of x. So we'll get the x terms all on the same side. And we'll subtract the non-x terms, 1.07 from both sides, and we end up with 9.63. And then we'll divide both sides by 12. And x works out to be 0.803. So now we have a value for x, and we have equilibrium expressions which represent concentrations that involve x. So let's just plug in. For H2 and I2, 1.07 minus x would be 1.07 minus 0.803. And for the hydroiodic acid, 1.07 plus 2 times 0.803. And we can work that through just a little bit. If we wanted to get actual numerical values, when you subtract, the concentration of hydrogen works out to be 0.267 molar. Same thing for the iodine concentration, 0.267. And let's see, 1.07 plus 2 times 0.803 would be 1.606. And that works out to be 2.67 molar. So now we have the concentration at equilibrium of H2, concentration at equilibrium of I2, and the concentration at equilibrium of HI. Notice that they're a factor of 10 apart. That's an interesting way that this problem worked out.